Hello, welcome to this second video in a short series about using MicMap tools. In the first video I explained a bit where to find the tool and what to download and how to install. So if you have not seen it yet, I suggest you might do so. And in this video I will go through a very simple example how basically we can use the MicMap tool and what are the output and what to expect as an output. So first, to do a mapping, what we need is a FASTQ file. In this case, I will just fabricate one as a very small example, so to get some data that I know will map somewhere. I have put the source of the data I used in this example.md file that you can open in the browser or in an editor. So I will just quickly grab the command I used from here and paste it here. So what we have in this short output file is just one region of chromosome 21 that happened to be probably expressed, so transcribed, but it is beside the point. It's just a section of the chromosome that I know exists. And what I have done is select one read that will map perfectly. So I have taken a short piece of sequence about from here to there, more or less, with one read going in the forward direction and the other read going from the reverse direction. So I have selected one which will map perfectly, one in which I have replaced one of the nucleotides in the read by an N, one pair where I have introduced a change in one of the nucleotides, one of the pair where I have introduced a deletion, so frame shift if you like, one pair where I have rendered one of the reads not mappable. So what happens then is one of the read will map, but the other cannot be mapped properly, so it will be half mapped, so to speak. One read which resembles what happened when we perform high C, so where restriction sites are used to cut the sequence in, for example, in this case, GATC, where position is GATC, the restriction enzyme will cut the sequence, and then these dangling sequence, if they are close by, they will get ligated, and so a chimera is formed. So there is a chimeric read read pair that will happen, and I have also produced one pair where both reads cannot be mapped, so they should be fully unmapped. So to generate these, I have put here in the file the region like this. So again, copy, paste here. So I have now created one file for R1, and similarly I will create one FASTQ file for R2. Copy and paste. Okay. So just to check, let's see what I have in the R1. So we expected, it seems to work. So that is a simple FASTQ file. If you don't know them, there is a group of 4 lines each time, with the first line being kind of a header. So in this case, I have fabricated something that resembles normal Illumina machine output. So this machine name and then some position and the sequencing slide. But you can also put, just instead of all this, you can just put 1 or 2 or something else. And I have added the code here, P, where I expect it will be a perfect match, N with the ends I introduced. So the N is here. This one with a mismatch, this one with a gap, this one with half map, this one with a chimera, and this last one, which I expect to be unmapped. When the MicMap tool runs, it will produce output files. If the output file where it expects to write already exists, it will not remove it first, it will simply add to it. The format of files we use can be concatenated together, so we can add more and more. So in principle, if you start fresh, it's a good idea to verify there is no leftover, so to speak. So let's remove what I think might still be there. So there, and then run the MicMap tool itself. I want to map it against the human genome. So that's the command. So MicMap. This is the definition of the content of the genome itself. This, for historical reason, will still have this parameter, which could be derived from the first one, but for the time being, it's still being said this way. And as I mentioned, we need them to be in this huge page file system for the things to run correctly. And I put some additional parameters simply because this is a very short file and I want to run it simply and just create, not have too many things run in parallel. Then I provide the FASTQ1 and FASTQ2 for the read pair, and the results, I want them to be in TMP and start with the name TST_B38. So I forgot. To do that, we should go in the container, otherwise it will not work well. So I had the command to go in the container a bit up, so sorry, I forgot to do it. So there. So just maybe back to the command itself. This specifies what file systems or what directories you will need to see from within the container. So in any case, you will see TMP and your home directory, but other places on the file system you will not see unless you ask Singularity to map them. So in this case, I ask it to map those 3 places. So the huge table file system, the data6, because that's where I have my reference data, and this, well, in this case I would not need it, but it doesn't hurt to be there. So let's go in Singularity, and now I can actually copy paste the command. So let's run it. Goes pretty fast, and if just want to see. So we see it has created a log file, and it has created these output files. So the format is the header we specified, then an underscore with a capital letter. If many things run in parallel, we could have an underscore A, an underscore B, C, etc. And then there is a format, so we have things on chromosome 21, we have things unmapped, and we have things half mapped, and we have some chimeric output. So MicMap will separate the different kind of outputs. And moreover, with the chromosomes, since, for example, chromosome 1 is much larger than chromosome 21, we have further split the large chromosome into sub-pieces. So the large chromosomes are split into 4 regions, or dubbed A, B, C, and D. And the smaller one, for example, 21, just have A. There is no B and C, but the A is still there. So that's why there are these additional A, B, C, and D to the chromosome name. And for example, if, of course, the numerical chromosome, it's easy. X is chromosome 23, Y is chromosome 24, etc. The decoy things have higher number, so it's only a numeric chromosome names that appear there. It's not a real name, so to say. To look what is in the file, we can use this GTL decompress command here. So this will output what is once mapped. So there are several, so needs again the definition of the genome that was used, the input file that we want to see, and we have to specify that we want to see the perfect matches, so with this -p. And the output we want to see as SAM, so that, for example, here, if we don't specify the output, it will output the FASTQ format. But of course, then you lose the mapping information. So we can do the same for the other. I have put the commands here that you can try out as well. Before using these things, we still need to sort them, because many of the tools later on expect the output to be sorted by chromosome position. So we have a simple tool that does this. Here I will do copy. So I'm telling the tool to the tool itself can do also some call with to see what are variants, but I don't want to do a call here. There is just too few reads. Nothing would be significant. So I say with the -c, don't do call, just do sort. D means delete the files once you have sorted them. And this is the name I used when I performed the MicMap step. And the tool expects things to be in TMP, but you can specify it's somewhere else if you had to do, but by default it's there. So let's just sort it. I had it there already, so let's remove. Let's start again. Let's make sure we remove everything. So do the mapping again. do sorting. So this sort is relatively verbose. It tells each file it's trying to sort, and in the end, if everything works, you should have this green line that says we have 7 reads in the input, which is what he had, and that's what we have in the output. And now we have this directory that's been created where it's basically the same as before, except we also have a separation between the perfect matches, the matches with ends, the matches with mismatches, and the matches with gaps. And we have the unmapped, the half-mapped, and the chimera. So in the further processing steps, when we do look for variants, we concentrate on just these reads. We don't take into account the unmapped reads, nor the half-mapped, nor the chimeric reads, only these ones to search for a single nucleotide and indels. That's where we look for them. Not shown here, we handle the case where normally we place a pair to its best matches. So if there is a single best match, that's where you expect it to go. If we find 2 equivalent matches, we record them, and then the file name would start with a capital M. So similar to this file, but with a capital M in the header. If there are more than 2, then they go into the unmapped. At this point, out of these files, we also can build a BAM file, because, for example, if we want to use GATK to do the calling, GATK doesn't know how to read this GTL file, so we produce a BAM file out of these. In the BAM file also we do not put the half-mapped and the unmapped, but we do put the single mapping. We do put the dual mapping as well. So the last thing I will show you is we can quickly visualize this output. So if you remember when I did a GTL decompress, oh it's going, so I have to look into the sorted version. So I have to look in the perfect, and I have to look in SAM. We've seen that it maps on chromosome 21 roughly near this position, so we can visualize these mappings with this SAM tools command. Copy, paste. So this is where it maps. So we have the perfect mapping was the first one. So this one on the top. It doesn't show the P, but anyway, that's the one. Then we see the one that had an N, maps there. If we scroll to the right, we hit the one I prepared with one mismatch here and there, and finally a bit further down, the one with the deletion. and the others will not appear because we only look at in these 4 categories. Let me check. Okay, so I think that's it for this part of the series. Bye-bye.